here we go. This is our change, and the hope is that when we recast our equation in terms of phi function, it will become the equation with linear coefficients. So let's do this. So first we compute the first derivative of psi function, which is obviously phi prime minus y phi multiplied by the exponential, and the second derivative. So we differentiate it as a product of two functions. So the first term gives us and the second term gives us just negative y multiplied by these braces. So, and this multiplication will give us additional factor 2 here from this factor, and one more factor plus y squared. Right. Now we should plug in this second derivative into our initial equation and see what's going to happen. So, yeah, right. So phi prime prime minus 2y phi prime and minus this term minus phi, plus y squared phi, of course, plus y squared phi. So this second derivative term minus y squared phi and plus 2e over omega phi. And of course, I cancelled both parts of this equation by this exponential term. And we see that the thing that we were hoping actually happened. This quadratic term cancelled. And finally, we have the equation with linear coefficients, which looks as follows. Phi prime prime minus 2y phi prime and plus 2e over omega minus 1 phi. Now let's denote this term, which is proportional to our energy, by 2 nu. It's a standard notation. And then this equation is reduced to so-called Harmonic equation. And now let's investigate the structure of this equation and its asymptotics. As you remember, we are interested in the bounded solution because we are looking for solutions which describe the oscillations of the particle in a potential well. So the wave function should be bounded. So phi function, well, actually it can grow for large y because it has this exponential prefactor, but its growth should be not greater than e to y squared over 2. Otherwise, the initial wave function will blow up. So far, so good. So now let's implement our scheme for solving differential equations with linear coefficients. So as you remember, we introduced these p and q polynomials. The p polynomials is, in our case, is just t squared plus 2 nu. And the q polynomial is minus 2t. Now we perform the integration. Which is, okay, let's write it down explicitly. And finally, the integral is minus t squared over 4 minus nu logarithm of t. As usual, we drop all the integration constants. They are irrelevant. And we write down our v function, which is simply e to yt minus t squared over 4 plus or minus new logarithm of t. But let's write it like this. And our z function, it's 1 over q, so it's 1 over t, up to factor -2, times this thing. So our z function is simply e2 minus t squared over 4 times 1 over t2 nu plus 1. Fine. And finally, our exact solution. So the exact solution is given in terms of the contour integral. So of z function, it's e2 yt minus t squared over 4 dt over t2 nu plus 1. And the contour should be chosen in such a way that the function assumes identical values. Again, the first thing we notice, we pay attention to, is that our v and z functions are multi-valued functions over the complex variable t. And the branch point is the origin in the complex plane of t. So now, how shall we position the branch cut? Well, it's up to us to choose. We just try different configurations. Usually, well, in many cases, this negative real axis works just fine. So let's draw our branch cut as our first try in the negative direction along the real axis. Now the contour. Well, first of all, we can't choose the closed contour because the only singular point in this case is our branch point, which is here, and we can't circle around the branch point due to the presence of the branch cut. So, but any other closed contour won't do because it will yield zero integral and trivial zero solution. So we have to choose the open contour. And now, how shall we position it? Well, first of all, the integral defining our exact solution should converge. So as usual, we study the asymptotic behavior of our integrand. And our integrand basically coincides with our v function. For example, for the convergence of the integrand, we require, if t becomes large during our contour, for example, we consider a contour with infinite legs, then this exponential should decay. And here in v function, we have the same kind of exponential. So the requirement of the decay of the exponential will give us correct contour because v function will assume identical values, which will be just zeros, and the integral will converge simultaneously. Great, so we just require that our exponential function vanishes. For large t, as usual, the second term, the quadratic term, dominates over the linear term. So we just require that t squared, the real part of t squared, is positive. We already encountered that kind of exponent functions many times before, and probably you remember the answer. The answer is that this condition gives us so-called angled regions in the complex plane, and the corresponding angles are pi/4 in both directions. So here are our allowed regions where the legs of the infinite contour should be placed for the integral to converge and for the function to vanish. Right. So now what would be our possible choice of the contour? For example, any contour. Oh, by the way, let's actually shade this region. Sorry, I forgot to do this. Any contour which starts at one allowed region and ends in another one will do. We can actually draw another contour which starts and ends in the same region, like this. But this won't do because we can position the contour entirely at plus infinity. And if we do so, because we can deform it, right? If we do so, our exponential function will vanish there, and then again our solution will become trivial, just 0. So our choice of the contour, reasonable choice, would be, for example, that kind of contour. Probably because it starts in the one allowed region and crosses to another one. It can't be deformed entirely to one or other infinity, because as we deform it, we will have to cross through this forbidden region, and this is forbidden. So the second possible choice would be the contour which starts, for example, at left infinity, circle around the branch cut, and returns to the left infinity. So these are two linear independent contours, which gives us two linear independent solutions of our differential equation. Well, one could argue that probably we could choose also the contour which lies below the branch cut. True, but this contour will simply yield complex conjugate solution to the initial one. So let's just choose this one and this one. Okay, so first let us investigate the behavior of the solution defined by this C1 contour. As you remember, we require that our total wave function decays at y tending to plus and minus infinity. So now our number one task is to explore the behavior of this integral at large and positive and negative values of y coordinate.